All right, in this video, I'll be covering definite integrals using U-Substitution. All of the examples I've been doing in the other parts to the section 4.5 videos dealt with indefinite integrals. And so I work an example out. So say we wanted to integrate the definite integral from 0 to 1 of x times x squared plus 1 cubed dx. And there's two approaches you can do. I went ahead and worked it out just to show each approach. The first approach is changing the limits of integration to reflect the change of variable. And so for a problem like this, I would let u be the stuff in parentheses as far as x squared plus 1, then taking the derivative du that would be equal to the derivative of x squared is 2x, and then the 1 goes away because that's a constant. So it's 2x, and then I attach the dx next to it so that I can substitute it into the integral. Now in the integral, I have x and dx. I don't have 2x dx. So I bring the 1/2 over with du so I multiply both sides by a half to get rid of the 2. So multiply by a half. So that way, when I multiply by a half, on the right side, I have the x dx part. And then I'll be substituting in 1/2 du. All right, that's what we've been doing up to this point. Now that something new is this part, changing the limits of integration. Our original limits are 0 and 1, but those are in terms of x. So I need to change them in terms of u. So what you do is you start with the first one, x is 0, substitute that in for x into what u is. I'm letting u be x squared plus 1, so plugging 0 in for x, that's 0 squared plus 1. So u is going to be 1 when x is 0. And then I change the other one, where x is 1, plug 1 in for x, so it would be 1 squared plus 1. So you get u is 2. All right, so now I've circled in green everything I'm going to plug into the integral. So our original integral from 0 to 1, and I reordered it so that you have the x squared plus 1 cubed and then the x dx part. So that way you know that's u, and this is going to be something involving du, which is 1/2 du. All right, the x dx part is 1/2 du. So that's where you see in yellow. So instead of x squared plus 1, you have u, and then it's cubed. And then instead of x dx, that's 1/2 du. Now that I also changed limits 0 and 1 to 1 and 2, since that's what we found above. All right, then I just integrate this. And so I factor out a half, and then I integrated u cubed. Well, that's u to the 3 plus 1 divided by 3 plus 1. So that's u to the 4th divided by 4. So I have 1/2 times u to the 4th over 4. Well, 1/2 times 1 over 4 is 1 over 8. So I went ahead and factored out the 1 over 8. So you get 1 over 8 times u to the 4th. And I should have wrote this, my limits of integration are 1 and 2. All right, I don't change the variable back in terms of x. I keep it with u because I've changed the limits of integration in respect to using u. So I go ahead and apply the fundamental theorem. So I do 1 over 8, and then in brackets, it would be the upper limit minus the antiderivative of the lower limit. So this is our f of 2 minus f of 1. All right, fundamental theorem of calculus. So 2 to the 4th minus 1, that's 15. So you get 15 times 1 over 8 is 15/8. All right, that's the first approach you can do. And that was changing the limits of integration. And when I change the limits of integration, I don't back substitute. And the indefinite integrals, we were back substituting. Now the second approach is to keep the limits of integration. And if you keep the limits of integration, you do have to back substitute. So what you see here is the same steps as above. I just don't change the limits of integration. All right, so this is all the same. So I have 1/8 times u to the 4th, and I keep the limits at 0 and 1. So now I back substitute what u was. U was x squared plus 1. So I have 1/8 times, in brackets, x squared plus 1 to the 4th, with the limits of integration 0 to 1. So if I keep the limits of integration, I don't change them, then I have to back substitute everything in terms of x. All right, then I apply the fundamental theorem. It's just this time my upper limit's 1, my lower limit's 0. So I'm doing f of 1 minus f of 0, plugging in for x. And you get the same answer, 15/8. Now, to me, it's easier to use the first approach because I guess for this particular example, they're about equal difficulty, but for future examples, you'll see that it might be just easier to use the first approach. Once you change the variable, also change the limits of integration, but do not back substitute. All right, so that's just to show you that there's two approaches. I'm going to use the first approach where I change limits of integration, because I think it's easier to plug in, because when you back substitute in this case, you get x squared plus 1, whereas before you just had u to the 4th. All right, so I'll be using the first approach, and these are 4 examples I'll be doing. All right, so number 61, we're integrating from -1 to 1 of x times x squared plus 1 cubed dx. So I'll let u be the more complicated stuff, the stuff in parentheses, the x squared plus 1. So u is x squared plus 1. Then taking the derivative, du, that's going to be 2x dx, since the derivative of x squared is 2x, and then the 1 goes away because that's a constant. But here I have just x dx, so I need to bring the 1/2 over, or sorry, I need to bring the 2 over by dividing by 2 or multiplying by 1/2. So when I multiply by 1/2, I get 1/2 du, and then the 2 goes away, so you have x dx. So I'm substituting u in for x squared plus 1, and then I'm substituting 1/2 du in for x dx. Now I need to change the limits of integration. The first limit is -1, the lower limit. And so if x is -1, u is -1 squared plus 1, and make sure to put the -1 in parentheses when you square it, because that'll give you +1 plus 1, which is going to be 2. And then changing the other one, you also get 2, because it's u is equal to 1 squared plus 1. So now I'm going to change the problem using my new limits of integration. They just happen to both be the same in this case. And then I'll reorder it. So, and this is a preference thing, I like to put what u is first. And that was x squared plus 1, and then cubed, and then I put the x dx. All right, so substituting stuff in. So that's going to be the -1 to 1. Those both happen to be 2 in this case, so we have 2 and 2. Then x squared plus 1, that is u. So that'll be u cubed. And then x dx, well, that's 1/2 du. And you could factor out the 1/2. So I have the integral of u cubed. So 1/2, and then -2, or sorry, 2 to 2. And then u cubed du. Now there's a property of definite integrals that if you were to do the reading in the textbook, notice I have the same limits of integration. And when you have the same limits of integration, like integrate from a to a of f of x dx, that's going to be 0. So the short answer to this is 0, because I have the same limits of integration. So our answer is going to be 0. Yeah, so if I have lower limit of integration is the same as the upper limit, the integral comes out to be 0. Okay, so I'll leave that up to you to determine it being 0 if you were to actually go through and integrate u cubed and then plug in the upper limit minus the lower limit into the antiderivative, but you'll get 0 because of this rule. All right, so that's that question. The next one, number 63. All right, so I have this as my integral. I'm going to go ahead and factor the 2 out in front of the integral. It'll be 2 times, and then the integral from 1 to 2 of x squared, and then the square root of x cubed plus 1, and then dx. So u is going to be the more complicated stuff, which is inside of the square root sign, the x cubed plus 1. Taking the derivative, du. Derivative of x cubed is 3x squared, and then the 1 goes away because that's a constant. So I have 3x squared dx. Now in the integral, I have x squared dx. So I need to divide by 3 or multiply by 1/3. So get 1/3 du is equal to x squared dx. All right, the 3 goes away when I'm multiplying 3 by 1/3. All right, so that's what I'm plugging in for x squared dx. I'm plugging this in for u. Now I need to change the limits of integration. All right, so the first one is 1. So if x is 1, u is going to be 1 cubed plus 1. So that's going to be 2. And then when x is 2, u is going to be 2 cubed plus 1. So that's going to be 9. All right, so these are my new limits of integration. So plugging all of this in, we get 2 times, and then the integral, instead of 1 to 2, So when x was 1, that changed to 2. When x was 2, that changed to 9. So I need to change it to 2 and then 9. I don't know what I just did there. Okay. All right, so I'm changing this to 2, that to 9. Now the x squared dx, I'm going to go ahead and put the square root stuff first. If I put the square root stuff first, that's going to be the square root of u. I'm not sure why the colors are doing what they did, but u is supposed to be in yellow. And then instead of x squared dx, that's 1/3 du. All right, now I'm going to factor out a third, but then I have the 2 in front, so I do 2 times the third is 2/3. So I have 2/3 integral from 2 to 9, and I'll write square root of u as u to the 1/2, and then du, and then I just integrate. Well, then that's going to be 2/3 times, when you do u to the 1/2 plus 1, divided by 1/2 plus 1. And then my limits are 2 and 9. One half plus 1 is 3/2. So I'm going to have 2/3 times u to the 3/2. And then you're dividing by 3/2. Well, that's the same thing as multiplying by 2/3. So it would be 2/3 u to the 3/2. Right, because dividing by 3/2 is the same thing as multiplying by its reciprocal. Now I'm going to factor out 4/9, and then focus on u to the 3/2. And then I apply the fundamental theorem of calculus. So this would be 4/9 times 9 to the 3/2 minus 2 to the 3/2. Now, if you put 9 to the 3/2 in the calculator, that comes out to be 27. Now, putting 2 to the 3/2 in the calculator, that doesn't come out to be a nice whole number. But knowing how rational exponents work, if I have a to the m divided by n, that's the same thing as the nth root of a to the m. Now, when you're dividing by 2, that's the same thing as taking the square root. So for 2 to the 3/2, I mean, that's technically like you could have the index be 2, but they don't write the 2 for square root, and then 2 cubed. So we have the square root of 8, which we can simplify that to be 2√2. All right, so we have 27 minus 2√2. And then you distribute the 4/9. So 4/9 times 27, that's going to be 12. And then minus 4/9 times 2√2, that's going to be, so 2 times 4 is 8, so it'll be minus 8/9. And then √2. All right, that's the exact format for the answer. All right, so again, I would try to use the calculator for 9 to the 3 halves. That gives me 27. But if you try 2 to the 3 halves, it's going to give you a decimal number. So it doesn't work out so nicely for the 2 to the 3 halves. But then using rational exponent rules, 2 to the 3 halves is the same thing as technically the second root of 2 to the third power. Well, they don't write the 2 right here because it's just understood to be 2 when you're taking the square root. All right, and that's it for this one. Number 65 for integrating from 0 to 4 of 1 over the square root of 2x plus 1 dx. I'm going to let u be what's in the square root sign, so the 2x plus 1 is going to be u. Taking the derivative of 2x plus 1, so du is going to equal, well, the derivative of x is 1, so that's 2 times 1, and then derivative of 1 is 0, so I have 2 times 1, which is 2, plus 0 is 2. So the derivative of 2x plus 1 is just 2, and then dx. Now in the integral, I have just dx. I don't have this 2. So I would multiply both sides by a half. And the left side you get 1/2 du. On the right side, 1/2 times 2 does basically cancel each other out. So then we have dx. So that way I can substitute 1/2 du in for the dx. And then 2x plus 1 in for u. So I still need to change my limits of integration. So for the first one is 0. If x is 0, u would be 2 times 0 plus 1. You get 1. And then when x is 4, u is going to be 2 times 4 plus 1. That's 9. So my new limits are 1 and 9. All right, so this will equal the integral from 1 to 9. And then 1 divided by the square root of u. And then instead of dx, that's 1/2 du. All right, so integrating this, I'd factor out the 1/2. Now I have 1 over the square root of u. Well, we know u is, square root of u is u to the 1/2. But since it's in the denominator, by rule of exponents, that's really u to the negative 1/2. So I'd write this as u to the negative 1/2, and then du. So integrating, so it's going to be u to the negative 1/2 plus 1, and then divided by negative 1/2 plus 1. And then my limits are 1 and 9. Well, negative 1/2 plus 1 is a half, so I have 1/2 times u to the 1/2. Well, and then divided by a half. But dividing by a half is the same thing as multiplying by 2. So really I have 2u to the 1/2. And then the 2's cancel out, so you just have u to the 1/2. Well, u to the 1/2 is the square root. But really this is the square root of u. From 1 to 9. So then I apply the fundamental theorem. Do the square root of 9 minus the square root of 1. All right, that's our capital F of 9, and then capital F of 1. So 3 minus 1 is 2. So our answer for this one is 2. right, so that's for that one. The next one, number 67, and this will be the last problem for this video. All right, so we have a good bit of stuff going on here. We have 1 over the square root of x, and then times the 1 plus square root of x in parentheses squared. Now these things are in the denominator. I'm going to go ahead and change these into negative exponents. So we know square root of x is x to the 1/2. So if I have it in the denominator, 1 over square root of x is x to the negative 1/2. So I'll have the integral 1 to 9, and that's x to the negative 1/2. All right, that takes care of the 1 over square root of x. And then I have 1 plus square root of x to the second power in the denominator. If I bring this up to the numerator, that becomes 1 plus square root of x to the negative 2. And yeah, so and dx. And square root of x, which we know square root of x is x to the 1/2. So I'm going to go ahead and write this as x to the 1/2. And I'm writing it like this because we're going to take the derivative and we're going to have to rewrite it anyways when we take its derivative. So square root of x is x to the 1/2. All right, so I rewrote the problem like this, so you'll see why we're going to do the substitution. So I'm going to let u be the stuff in parentheses. 1 plus x to the 1/2. So du. Well, the 1 goes away because that's a constant. X to the 1/2, that changes into 1/2 x. And you do 1/2 minus 1, and then dx. 1/2 minus 1 is negative 1/2. So I have the x to negative 1/2, and I have the dx. I don't have is the 1/2. So I'm going to multiply both sides by 2 to get rid of the 1/2. So you have 2 du equal to, and then 2 times 1/2, those divide each other out. So you just get x to the negative 1/2 dx. So the 2 du is what I plug in for x to the negative 1/2 dx. And then I'm letting u be what's in the parentheses. So I need to change my limits. The first one is 1. So if x is 1, that means u is equal to 1 plus 1 to the 1/2. Well, 1 to the 1/2 is the square root of 1. So you could just write it as 1 plus the square root of 1. All right, so that's 2. The next limit is 9. So if x is 9, that's u equal to 1 plus 9 to the 1/2. And again, raising something to the 1/2 is taking the square root. So really this is 1 plus the square root of 9. Square root of 9 is 3. 3 plus 1 is 4. So my new limits are 2 and 4. All right, so substituting everything in, and I guess I'll go ahead and write the integral over again, and then I'll put the x1 plus x to the 1/2 negative 2 first, and then the x to the negative 1/2 dx. All right, so we know this is u, And we know that x to the negative 1/2 dx is 2 du. All right. And then we changed our limits. So 2 is going to go in the spot for 1. 4 is going to go in the spot for 9. So that's going to make this 2 to 4, and then u to the negative 2, and then 2 du. Now I factor out the 2. And then integrate u to the negative 2. So that's going to be 2 times, and then it's u to the negative 2 plus 1, which is negative 1. All right, so I have 2 divided by negative 1 is negative 2. So I'm going to factor out the negative 2 in front. And then u to the negative 1. And then 2 to 4. We know u to the negative 1 is the same thing as 1 over u. This is negative 2 times 1 over u, and then 2 to 4. So now I apply the fundamental theorem. So plugging in 4, that's 1/4, and then plugging in 2, that's minus 1/2. All right, so that's going to give us negative 2 times negative 1/4. All right, so that's going to be positive 1/2. All right, so that's it for this one, and that was the last example. So I rewrote the integral so that I have negative exponents. So when I do the substitution, it's a little bit easier to do the substitution. I still let u be what's in the parentheses, the 1 plus square root of x, which is the same thing as 1 plus x to the 1/2. And taking the derivative of that gives me 1/2 x to the negative 1/2. So the x to the negative 1/2, that's the same as the 1 over square root of x. So that's why I wrote it as x to the negative 1/2, because when I substitute stuff in, I can plug in 2 du in for x to the negative 1/2 dx. All right, and then I just change the limits and then integrate it. All right, so that's it for section 4.5. I'll be starting chapter 5 in the next videos.